moment curvature relation. So usually we'll say M phi. So M is your moment and phi is the curvature. So we have already discussed what the equation for curvature. We have discussed in the strength of material. The curvature is given by 1 by radius of curvature. So this equation we have studied in the mathematics. This is it is equal to 1 by, so 1 by, sorry, not 1. It is equal to d square y by d square y by dx square. Okay, d square y by dx square divided by 1 plus d square y by dx square the whole square. Three by 2. Okay, so that is equal to, so this is, we can approximately, you can take it as, or you will take it as d square y by dx square. That is what you have done in all double integration method. Everywhere we have used this approximation. So because I can write like this, 1 by r, that is your curvature actually. That is equal to m square d square y by dx square. Okay, so phi is your curvature. Because we can say that so what is this y and x actually? This is your maybe beam. Okay, and maybe this is my x and y. So once it loaded, it is going to deform. So this is your y. Because this vertical displacement is y and this is my x. Okay, and dy by dx means your slope at any point in the curve, and d square y by dx square, that is second derivative, that is your curvature. Okay, and actually 1 by r, where it's coming, this 1 by r is coming from your pure bending formula. Okay, also you can write 1 by r, that is your curvature, that is equal to, so m by ei. Okay, that is your curvature. All are same. Okay, so m by a is known as curvature, that is equal to 1 by r, and that is equal to d square y by dx square. So now I can write m is equal to your bending moment and curvature. What is the relation? M is equal to ei times your phi. Okay. So what is ei? Ei is a constant. When you, especially when your structure is in the linear elastic region, your ei is a constant. Moment of inertia is a constant for a section, and E is the Young's modulus, that is a constant. Okay, that is why I can draw a graph, something like your maybe stress strain relation or load deformation curve, something like that. I can draw a curve. Okay, m is equal to ei into phi, and this is constant, ei equal to constant. So ei is equal to constant in linear elastic region. Okay, as long as your loading is linear elastic, then your ei will be constant. Because why I'm saying is, if your the structure is going to non-linear range, then actual case what will happen? There may be some cracking in your concrete beam angle. There will be some cracks. So once the crack is coming, your moment of inertia will be reducing. You have to take the moment of inertia of uncracked part only. Okay, that is why this ei will be reducing once it is going to the non-linear range. So that is what happening in the real structure. So that is why specifically ei will be taking constant only for the linear elastic region. So in linear range means there is no cracking in the member. So it is just deforming, and once you remove the load, it can come back to the initial position. So that is the idea. So if you take your moment in the y-axis and if you take your curvature in your x-axis, initially it will be a straight line. It is proposed in the linear range. It is going to be proposed like this. It will be like straight line. Then there will be a curve transition, and then it will go like this. Okay, and this is actually let me, maybe I have to take this axis. So this is my bending moment. Okay, and and up to some point it is a linear, so its corresponding moment, that is your actually your my yield moment. Okay, and this moment corresponding to this, after that there is an increase of moment, that is your plastic moment. It has your section has reached completely yielded zone. Like the cross section, all the fibers has reached the yield stress, so the corresponding moment is MB. After that there is an increase. Okay, and this part we can say that your curvature is, I will say curvature is infinity, and this point indicate like this. If you have a beam, if you take a simply supported beam, so let us apply point load. So it is going to deform initially linear, initially in the elastic zone. You are increasing the load, so the deflection will increase, and that finally the plastic hinge is formed. So it will become, there is no bending. It is like a it will become straight. Okay, and this is your MP. So initially you have the elastic region. So this is my deflection zone. Okay. So so the at the plastic, like once the plastic hinge is formed, your moment has reached MB, and then at the plastic hinge you can say that your curvature is infinity. Okay. After that you don't need to increase the load. You have to, if you maintain that load, the member will not have any, actually the member it cannot take any more load after that. Okay, and without applying any moment, it will just, this part can, it will rotate, it will not have any resistance against rotation. Okay, without increasing the moment, it will just, it can rotate because it will not have any resistance. And if you maintain that moment, or if you maintain that moment at that state, it will it curvature will keep on increasing. Okay, that is indicating your collapse stage finally actually. Okay, that is what this diagram is saying. This is your moment curvature curve. Initially it will be linear, and up to some point that peak value is a yield moment. After that we have a can say we have a at the transition. So maybe I can draw the corresponding stress diagram, then it will maybe clear. And this is your region, that is your elastic. So what is the corresponding stress diagram? It will be like this. Okay. So let me 1, 2. So 1, 2, that is a elastic, and let me call 2, 3. In this 2, 3, what is happening? Your section is partially plastic and partially elastic. So the stress diagram will be something like this. Okay. The stress diagram will be something like this, and maybe 3, 4, or 3 from here onward it is fully plastic. The stress diagram will be like this. Okay, and corresponding moment is yield moment, and here we have a transition. The section will be elastoplastic, and here the section will be fully plastic. Okay, so we have, this is your moment curvature relation. It is like your stress strain diagram only. The stress strain diagram we have, this is my stress and this is my strain. So we have the stress strain diagram initially linear, then it is plastic. Okay, and okay, similar to that we have the, this curve is the moment curvature relation. Okay, and so we can draw this for maybe for our rectangular section. So if you draw it for the rectangular section, it will be we can say that this is my moment. Okay, this is my bending moment, and this is our curvature. Okay, and let us take a rectangular section. If the cross section may be rectangular, let us take the cross section rectangular, and this is the neutral axis. This is the neutral axis. Okay, and initially it will be elastic. Okay, it is elastic. Okay, so this is the critical stage. Your extreme fiber stress are sigma y. So the graph will be like this, initially straight, then we have a small curve, then it is your constant. Okay, so this is my, let us say this is, if you take this is this moment, so this moment is MP and this moment is My. Okay, this is my phi curvature, and this corresponding curvature you can say that this is your curvature at yield point phi y, you can say. So let me call this point is 1, this point is 2, okay, and this is origin, and let me somewhere here 3. So in this region 0 to 1, this is your the stress diagram, and after that it will become it partially elastic, partially plastic. So partially elastic, partially plastic. So elastic, then it is plastic, and this is in 1 2. Okay, and the next stage will be fully plastic. Next stage will be fully plastic. 2 3, that is fully plastic. Okay, so now I can this is again it is what is the MB value in this case? MB will be equal to, in terms of My, that is 1.5 times My, because the shape factor for your rectangular section, that is equal to 1.5. Okay, that is again this is also same thing whatever we have discussed in the previous slide, that one only M5 curve. Okay, moment curvature relation. So I can make it is non-dimensional, like, and here we have moment maybe in kilonewton meter in this axis, and here we have curvature. Okay, here we have curvature in 1 by meter inverse unit. Okay. So here, okay, I think I should write. So up to 0 to 1, 0 to 1 in this region, your moment is proportional to curvature. Okay. So I can also maybe we can also write like uh, okay. Okay, so moment is proportional to curvature. That is your elastic. This is your elastic. And 1 to 2, 1 to 2, what is happening? 1 to 2 with further increase of bending moment. With further increase of bending moment, the curvature increases. The curvature increases at a faster rate. At a faster rate. So that is indicating. So indicating yield spread. Okay, yield is spreading into other fibers, other inside fibers. Okay, so because what is the curvature equation? M by EI. So if you are increasing the moment, your curvature will be increasing. In this region, both are increasing at the same rate. Moment is increasing at the same rate, your curvature is increasing. So if you increase moment here, same increase in curvature. Okay, but in the region 1 to 2, here you can see that this slope is reducing. The slope of this curve is less than this part. That indicating the less increase of moment, your curvature increase will be more. Okay, that is because your curve is becoming flat, right? So the less increase of moment, the curvature increasing at a faster rate. The curvature increases at a faster rate, indicating the yield is spreading into the other inside fibers. That is what happening here. The inside fibers are getting yielded. Okay, and then I have 2 3. 2 3. Here you can see that as the moment attains fully plastic, the curvature tends to infinity. Curvature tends to infinity. So that is indicating this graph is just going straight. That means without any change of moment, this curvature is just keep on increasing. Okay, so that indicates the plastic hinge is formed. Okay, as the moment attains fully plastic, So as the moment attains fully plastic, the curvature tends to infinity. Okay, so that is about this moment curvature relation, and many times that this moment curvature relation also we will idealize. So this is actual moment curvature initially state, then we have a curve, then it is going to this horizontal line, something like this. So maybe like this. So this moment curvature relation also we will idealize sometimes, like this is your m, it is your phi. So I can idealize this one also like this. Draw the extend this straight line and extend this straight line. So like our stress strain diagram we can idealize. Similarly this the moment curvature relation also we can idealize. So I can extend this straight line and extend this straight line, and it will join at this point. Okay, so this idealized moment curvature relation also we are using sometimes. Okay, it is also will be used. Instead of this one, we can also draw like this also, M phi curve. Okay. So this is for the rectangular section, and here moment is in some unit and your phi is in some unit. Okay, so I can also make this moment curvature relation or this graph in a non-dimensional form. So I can just divide this moment value with a moment value with a yield moment, and I can divide this curvature value with phi y. Okay, if I do that, it will become like this: m by my moment values are dividing with your yield moment, and all the curvature values are dividing with your curvature at yield point phi y. Okay, and this is your, I can say, the non-dimensional curvature moment curvature relation. Non-dimensional moment curvature curve. Okay, because here there is no unit, it is like 1, 1.5 only values are there. So same thing, now it will be, this part will be like this, it will be, this point will become 1 because we are dividing all the values with my. So this will be my by my, this will be phi y by phi y. Okay, the value phi at this point is phi y, so we are dividing that with phi y. Okay, so we are dividing all the values of phi with phi y here, and here I am dividing the m with my. So it will become 1, it is also becoming 1. This indicates the elastic region, it is a elastoplastic, and then it is a plastic. Okay, so this is phi is equal to infinity. So it is the same thing, moment curvature your graph. Okay, graph in non-dimensional form. Okay, yeah. So that is what here also, okay, in this diagram, that is what you have to understand. The curvature is becoming infinity at that point. Okay, at that plastic hinge, your curvature is becoming infinity. That indicates without any change of moment, this curvature is keep on just increasing. Or you can say that in more realistic way, you can say that with very minute change of bending moment, your curvature will have large increase. So that is the meaning. Curvature is saying infinity. That is the meaning. Okay, that is the mean that you can show in the form of graph, that is the moment curvature relation. Okay, so this is in the non-dimensional form, usually we will draw like this only. So this can be drawn for other sections also, because it is for rectangular section, that is why this value is 1.5. If it is for a triangular section, this value will be 2.34. Okay, this will be 1, this will be 2.34, and actually the shape factor that is indicating this gap for this. Okay, if your shape factor is higher, then we can say that your difference between yield moment and plastic moment, that there will be this transition region may be more. Okay, this will be higher. So that is one thing I want to discuss, the moment curvature relation. So okay, so that is already that is, I think, okay, that much only required. So next we'll go to basic principles of plastic analysis. Okay, after that we'll go to the theorems of plastic analysis. So next we will see basic principles of plastic analysis. basic principles of plastic analysis. Okay, before that, let me ask, what are the basic principles of elastic analysis? Principles of the,
Stress is proportional to strain.
okay. So there are three theorems or three principles, I would say. So one is the stress strain relation, and so one is your equilibrium. One is your equilibrium. One is your equilibrium condition, and then second one is the compatibility, and third one is the stress strain relation. Stress strain relation. Okay, these are the basic principles we will be using. So we make use of these three principles in order to solve any problems with the elastic theory. So similarly, we have I would say basic principles of plastic analysis. Basic principles of plastic analysis. And the first condition is, I will just write first, then I will explain it. Okay. The first one is a mechanism. First one is a mechanism. Mechanism, and second one is your equilibrium. First one is, let us write mechanism condition, and second one is your equilibrium condition. Equilibrium condition, and third one is the yield condition. Okay. So what do you mean by mechanism condition? So mechanism condition, so that means we can say that at failure, it will form a mechanism actually. Suppose if we have a simply supported beam, so I will discuss this detail. Okay, mechanism, we'll see types of mechanism and all. For the time being, you can suppose we have a simply supported beam and we have some loading, maybe point load. So at the collapse stage, what will happen? A plastic hinge will be forming at the center, and once the plastic hinge is formed, then it is a mechanism, and I would say this is a mechanism. So once the plastic hinge is formed, in this case, only one plastic hinge is required to form a mechanism. Or you can say that by the formation of one plastic hinge, this structure will convert into a mechanism. Okay. So mechanism means you can say that it is a stage of a structure. It is a stage, maybe you can say that your structure cannot resist any more load. Okay. So that indicates collapse. It is going to collapse. So once the mechanism has formed, that means it is going to collapse very soon. Okay. So maybe I will write that sentence first. It is a stage. So the structure cannot the the structure cannot resist any more load. Resist any more load. So that is what we can say in this figure also. So I have two hinge support, and once you provide once you have a hinge in the in between the support, once you have hinge in the span, what will happen? After that, if you apply any small load, it will not able to take that load. It cannot transfer that load. It will just rotate like this. It will just rotate like a rigid bar. Okay, that is one of the mechanism. Okay. Okay, I will just write down one sentence, then I will explain it later on. So the mechanism, so at the ultimate load, number of plastic hinges must be the number of plastic hinges until I will explain it later on. Okay, must be just enough to form a mechanism. Okay, so I can say, for example, in a simply supported beam, so in a simply supported beam, only one plastic hinge is required to form a mechanism. Only one plastic hinge is required to form a mechanism. So I know that part may not be clear right now. I mean, how many plastic hinges are required and where the plastic hinge will form. That part we have to discuss in detail. Okay, that we'll discuss after this. For the time being, you have to understand this much only, because in the plastic analysis, what we are doing is we are analyzing your structure at the collapse stage, or we are finding out how much load it can take before collapse, or what is the value of collapse load for a given structure. That is what we are doing in the plastic analysis. That is why while doing the plastic analysis, first condition is the mechanism condition. The mechanism must be formed. Your analysis should be at that stage. Then only you will get the collapse load. Because after this, why we are doing this plastic analysis, we have to find out what is the plastic moment capacity, or we have to find what is the collapse load. So that is why at the ultimate load, the number of plastic hinges must be just enough to form mechanism. For a simple structure like a simply supported beam, you need only one plastic hinge. Then it will become a mechanism. So I will be analyzing at this stage. That is the first condition. It must be satisfied. And second condition is equilibrium. And whether it is plastic or elastic analysis, your equilibrium condition must be satisfied anyway. Anyway, your forces, moment, everything must be in equilibrium. The equilibrium condition is at any stage, equilibrium condition must be satisfied. So that is a common condition you can say between the elastic and plastic analysis. And equilibrium condition means simple: sum of moments and forces. Sum of moments and forces acting for sum of moments and forces acting on it, you can say. Okay. Both external and internal. That is must be equal to 0. That is the meaning of equilibrium condition. And the next one is the yield condition. The yield condition means, so let me write, the sum of yield condition means the plastic moment must, I will write, then I will plastic the plastic moment must not exceed anywhere in the beam or anywhere in the structure. That means the moment at any point in the structure should not exceed NB. That is the meaning of yield condition. Okay, that is the meaning of yield condition. That means your section must have yielded. Like this is the maximum moment. Okay, so this should not exceed at any point in the structure. So these three conditions must be satisfied in the plastic analysis. Okay, these three principles, I would say together, we will be calling uniqueness theorem. Okay, so these three principles together called uniqueness theorem. Okay, so we'll come to that. We'll discuss this. Okay, maybe in the next slide. So finally, in any problem, the solution has to satisfy these three conditions. Okay, and that solution that will give you a unique solution. Okay, so finally in our plastic analysis we have three conditions. The first one is mechanism condition, and second one is the equilibrium, and third one is your yield. Okay, and simple way, like equilibrium condition means your forces and moment acting on the structure must be in equilibrium, must be summation. If you take a internal and external moment sum, it will be zero. And mechanical condition means at the state while analyzing the structure at the ultimate load, then there should be the number of plastic hinges must be uh, enough to form the mechanism. For example, in this case, I need only one plastic hinge, so I should take only one plastic hinge for the analysis of this simply supported beam. Okay, there should not be too many hinge, or there should not be less than one hinge. Okay, that is the meaning. And yield condition means at any cross section, your moment should not exceed your MP. Moment should be less than or equal to MP. Okay, not less than. Yield condition means moment must be equal to MP, I would say. Moment must be equal to MP. That is the meaning of yield condition. Okay. And the three conditions, the first one is the mechanism must be formed, and all the forces, everything must be in equilibrium. And third condition, your moment should be equal to MP. So if all the three conditions satisfied, then it will give a unique solution. So then it will give a unique solution. Okay, like elastic analysis, it will always give a unique solution, but here we have different theorems. So some theorem will give you a solution which is more than the actual solution. Okay, and some theorem will give you a solution in the sense collapse load. Suppose if you are finding out the collapse load, and some theorem will give you collapse load more than the actual collapse load. So some theorem will give you collapse load which is less than the actual collapse load. Okay, but if all the three conditions are satisfied, then you will get a single value. You will get the actual collapse load, then only you will get. Okay, so there are some one type of solution which will satisfy these two conditions only. Out of these three, mechanical condition and equilibrium condition will be satisfied, and that solution is known as upper bound solution. So upper bound solution. Okay, and another type is the equilibrium condition and the yield condition are satisfied. Equilibrium condition and yield condition, and that solution in the sense we are finding out the collapse load. Okay, equilibrium condition and yield condition, these two condition has been satisfied, then that solution is called lower bound solution. That solution is known as lower bound solution. So usually we will write LBS. Okay, it is a upper bound solution. Okay, so upper bound solution, it will give you the load that will be more than your collapse load, and this will give you the load. It may be more, greater than or equal to, can be equal also. And this lower bound solution means it will give you the collapse load that will be less than or equal to the actual collapse load. Okay, so let us discuss that maybe a little more. Lower bound solution. Lower bound solution. So what is the lower bound solution? In the both the case, your equilibrium condition must be satisfied anyway. That is compulsory. So it should satisfy equilibrium condition. But mechanism condition, equilibrium condition satisfied, but yield condition not satisfied. That's the type of solution is known as upper bound solution. And whereas if you come to the lower bound solution, equilibrium condition anyway it has to satisfy, and the yield condition has been satisfied, but your mechanism condition is not satisfied. Okay, so let me write that anyway here. So LBS, that means, what does it mean? Like yield and equilibrium. When you come to the problem, that is very easy, but the theorems also you have to understand. So this is usually we'll find it a bit difficult to understand. Maybe you are reading from the textbook. So, but when you come to the problem, that is it is easy. Okay, so solving the problems are not difficult. The lower bound solution yield and equilibrium condition is satisfied, but mechanism has not formed. So that means so one more example I'll give you for the mechanism. For it, maybe I think I should have explained the mechanism first. Maybe so if you take a fixed B, okay, and if you apply some load, point load, okay, and if you draw the moment diagram, this will be like this. So we'll have some moment at the peak moment at the fixed support. Also we have a peak moment at the midspan also. Okay. For this structure actually to form a mechanism to reach a collapse stage. So by the formation of one plastic hinge, it is not sufficient. Even though I have a hinge at the midspan and both the ends are fixed, it is able to carry the load. For this particular case, to form a mechanism, there should be three plastic hinges. Okay, then only it will form a mechanism. Actually, this, and both the fixed end will have a two plastic hinge, and one is at the midspan. Okay, this is the mechanism. For to form the mechanism for a fixed beam, we need three plastic hinges. Okay, but whereas in the case of simply supported beam, with the formation of only one plastic hinge, it will become mechanism. The mechanism means it is a stage of a structure. You can say that it cannot take any more load. That is indicating collapse stage. Okay, so that is the mechanism. We have to discuss this anyway. And okay, so lower bound solution yield and equilibrium condition has been satisfied, but mechanism has not formed. Mechanism has not formed. Okay, that means in structure, so in structure still some capacity left. Capacity left. Okay, so that is why we will get a solution in this case. So we can let me explain little more. So lower bound solution means equilibrium condition and yield condition has been satisfied, but mechanism has not formed. So that means maybe for example in this case I need three plastic hinges to form mechanism. Okay, but here we are solving as per the lower bound theorem. Only these two conditions are satisfied. The mechanism is not yet formed. That means your structure it can take some more load. Okay, that is the meaning, because once the mechanism is formed, that is only indicating your collapse stage. Okay, so with the formation of only one plastic hinge, your fixed beam will not collapse. Okay, to collapse, it should form a mechanism first. For the mechanism, it should develop three plastic hinge. Okay, that is why here it can take some more load, some capacity is still there in the beam. Okay, that is why you are getting your load as a collapse load. That load will be less than your actual collapse load. Okay, so we are getting a solution in your lower bound solution. That solution is actually lower than it should be. Lower than it should be. Okay, that is because of this. And similarly, in upper bound solution, just opposite. So upper bound solution. So now here by using this in this case we will get a solution, and mechanism is already formed, and equilibrium anyway it is also satisfied. Okay, uh, but yield condition not satisfied. That means in this case the mechanism is formed. So you have to just read it. Okay, after that maybe after the class you have to just read any textbook this part, then it may be clear. if it is not clear. Okay, mechanism is already formed in the upper bound solution, and equilibrium condition. So anyway, it has to satisfy. So that is common condition for both upper bound and lower bound solution. But your moment, as per the yield condition, your moment should be equal to mb. That is your yield condition indicating m is equal to mb. This condition is not satisfied in the upper bound solution. Okay, because maybe for example your structure may be too slender. I would say the structure may be too slender. So before reaching this level, it is collapsed somehow. It may collapse somehow. Okay, something like that. So that is why this condition is not satisfied in the upper bound solution. Okay, so actually we will use both the theorem or both the method, and if finally we will take a lower value as your solution if it is not matching. And if any solution satisfying all the three conditions, that will give you a unique solution for your structure. Okay, a unique solution means that will give you the correct answer. Okay, so how to solve in how to apply this in the problem, that we will discuss. So maybe we will discuss later on again upper bound and lower bound theorem. That it maybe we will discuss little more in detail. Okay, so you may have understood something and you may have some doubts also. Let us keep it there. Anyway, we will clarify that. If it is not something, if it is not clear, we will clarify it while discussing about the upper bound and lower bound theorems again. Okay. So now we will go to some condition for forming the mechanism. How the mechanism is forming, and what are the different types of mechanisms, and where the plastic hinges can form. Okay, and that part we have to discuss again. After that, we'll again come back to upper bound and lower bound theorem. And then we can go to the numericals. Okay, so now I have given you two examples. One is simply supported beam. I need only one hinge. I need only one plastic hinge to form the mechanism. But if you have a fixed beam, you need three plastic hinges. How to decide that? That part we'll discuss. Okay. After discussing mechanism, maybe that time it may be better. You can come back to upper bound and lower bound theorem. Okay. The next one is the this is also important concept, mechanism condition. And from here also the short answer type question will be asking in your exams, GATE and ES exam. How many mechanisms should be there? Something like that. Okay. So mechanism condition. Okay, so mechanism means it is a state of a structure where it cannot resist any more load. That indicates collapse. Okay, so that means collapse load. So we will do a lot of numericals after this. Then it will be clear. Everything will be clear. So collapse load or ultimate load, what are saying, is reached when a mechanism is formed. So when a mechanism is formed. Okay. So how many number of plastic hinges are required to form a mechanism? Okay. The number of plastic hinges required to form the mechanism. That is n is equal to, I would say, ds plus 1. That is simple formula. It will give you the number of plastic hinges, and n is equal to ds plus 1, and where your ds is nothing but your degree of static indeterminacy. Degree of static indeterminacy. It is a simple formula. It will give you how many plastic hinges are required to convert a structure into a mechanism. Okay. So that means if we have a simply supported beam, the degree of static indeterminacy is 0. It is statically determinate. So the number of hinges required is 1, 0 plus 1. So wherever your moment is maximum, that point the one hinge will be forming. Suppose if you have a concentrated load acting at here, the hinge will be forming at that location. So with the formation of only one plastic hinge, it will become a mechanism. It will become a mechanism. That means at once the hinge has one plastic hinge is formed in the simply supported beam, it will not be able to take any more load. That indicates it has collapsed. So we have to limit your load up to that point or before that point. So for one more example, I'll give you fixed beam, so which I was discussing in the previous slide. So I have a fixed beam. So we have some loading also, let us say UDL. And here the static indeterminacy is 2. So the number of plastic hinges are 2 plus 1 and ds plus 1, that is 3. So where the plastic hinge will form, a simple, we will discuss that where the possible location of plastic hinges, that we will discuss in the coming slide. But right now I can say that 3 plastic hinges will form, but 2 will be at the support in this case. And the next one will be wherever the moment is maximum, there it will form. Then it will collapse. This is the collapse mechanism. In this case, this will be your mechanism. It will be like this. Okay. So here I have 1, 2 and 3. So for a fixed beam, you need 3 plastic hinges. Then only it will become mechanism. This is actually what is happening when your structure is going to when your structure is in the plastic zone. Okay, so it is all applicable. Suppose if you have multi-story building frame, so it will be having indeterminacy will be huge, right? The static indeterminacy will be very high. That it is because it is highly indeterminate. But that means for a building structure, framed structure, I would say, this to collapse this, it has to form so many mechanisms, for lot of plastic hinges, not only one or two. It has to form lot of plastic hinges like this. So after forming the plastic hinges, it will form mechanism. Then only it is going to collapse. Okay, so this is what happening in the case of building structure. So all these plastic hinges will not form simultaneously. That is also another important point. Okay. So first, wherever the moment is getting peak, the plastic hinge will form at that point, because it is actually happening. We are doing this nonlinear analysis for the building frame, especially for the seismic analysis actually. Suppose we have seismic analysis, we have the lateral force. Your building may it may sway. It will go something like it will oscillate, or it will go like this. Okay, so what will happen? It will go like this. Usually, if you have a horizontal sway like this, mostly your moment will be maximum where the moment is maximum at the beam column joint. There the plastic hinge will start forming. First it will form somewhere here, for example. Then this location cannot take any more load, and this will distribute the load to the other joint. And finally, the hinge will forming there also. Finally, this plastic hinge will be spreading to the other location. Finally, so many plastic hinge will be forming in the structure, and then it will form mechanism. Once it reach that mechanism stage, then it will just collapse. The column joint will collapse. Okay, so finally your overall structure will be collapsed. Okay, but till the suppose I have the indeterminacy let us say 100. In this case, I have a large building frame and static indeterminacy is 100. So as per our theory, we can say that now there should be 101 plastic hinges in, for example. Okay, so finally, initially one, two, some plastic hinges started forming. Then it will not, that joint will not take any load. It will distribute to the other joints, and finally all the joints will be reaching the plastic hinge. Okay, all the joints, the plastic hinge will be forming, and then finally the mechanism will be forming. Then your structure will be going to collapse. Okay, so up to that point, it will be able to distribute the load to the other joints. Okay, that is advantage because we have a lot of indeterminacy. So even though one or two joints are collapsed or joints the plastic heat has formed, still it will stand. It can take the load by distributing to the other joints. Okay, so finally anyway, this is your equation that will give you the number of plastic hinges required to form the mechanism, that is equal to ds plus 1.
Sir, I cannot understand the frame.
Frame I will because this frame we will discuss later. Okay, the numerical part I will be solving the frame.
Okay, sir.
I was just trying to give you some applications or some examples. Just to know that these things are we are using in the seismic analysis center. Okay, and we will discuss the frame, not the building frame. Building frame we have to go for some software like it has. So small frame we will do the analysis. Then I will explain. Okay. So I'm just telling all these things are not required right now, but if you get something or you should know those things are there, so you can read it further. For that purpose only I just told you all those things. But we'll solve it in, we'll solve my numerical example. Maybe I will show you the large frame maybe later on in some software that I will show you later on. Okay, so yeah. So this is the thing you have to understand. For that only I was just giving you some examples. The number of plastic hinges required to form the mechanism, that is the degree of static indeterminacy plus 1. Okay, this many plastic hinges are required to convert your structure into a mechanism. So what is mechanism? That is indicating collapse stage. And corresponding to mechanism, we can find the corresponding load will be your collapse load. We can say in reverse also. Once the load reaches the collapse load, it will become mechanism. Okay, you can say in multiple ways. And okay, this is the number of plastic hinges required to form mechanism. So anyway, all equilibrium conditions should be satisfied. All equilibrium conditions must be satisfied. All equilibrium conditions should be satisfied. Okay. And the next is yield condition. Yield condition. This is just repeating whatever we have discussed. I am just writing everything here. Yield condition that indicates bending moment at any section. Maybe in simple one line I can write bending moment at any section less than or equal to MP. Okay, and the portion between the plastic hinges. Portion between the plastic hinges between the plastic hinges are moving without an increase of load. Okay, are moving without an increase of load. So that is what we'll be calling mechanism. Okay, the mechanism means like this. So between two plastic hinges, this part is just it will be straight. It is like a rigid bar. It will just keep on rotating. If you apply some load, if you have to just maintain the load, it will not resist that load finally. Okay, that is what I was trying to write here. Okay, this is the condition. This many hinges are should be there to form the mechanism. That is a degree of static indeterminacy plus 1. Okay, that means suppose if we have a highly indeterminate structure, that will be able to take more load, because this plastic hinges will not all the plastic hinges will not form together. It will form gradually, and if you have a very high indeterminate structure, so it can take more load, because to form the mechanism we need large number of plastic hinges, so that will take some time to form. We have to distribute the load one by one. It will take some time. Okay, after that only it is going to collapse. So when you come to the types of mechanism, so the next we have to discuss the different types of mechanisms. So there are the next one is types of mechanism. First one is the simple case beam mechanism. Beam. So beam mechanism. Okay, so means all the loaded span behave as a beam mechanism. Okay, so like this simply supported beam. So we have a point load at the center. So static indeterminacy will be equal to 0, and number of plastic hinges, that is 0 plus 1 is equal to 1. Okay, that means, so the mechanism will be like this. This is the beam mechanism in this case. So we need one plastic hinge. Okay, and next one, let us take a propped cantilever beam. One end is fixed, and this is pinned, simply support one end, and we have some load. So in this case, so we have static indeterminacy will be 1. So the number of plastic hinges are 1 plus 1, 2. So 2 plastic hinges will be formed. One will be at the fixed joint and one will be below at the load point. So this is the collapse mechanism. 1, 2 plastic hinges. So another simple example, you have a fixed beam, point load. So here we need static indeterminacy is 2, and number of plastic hinges required to form the mechanism, that is 2 plus 1, that is equal to 3. Okay, so this is equal to here one hinge and here one hinge. So after forming 3 hinges, then only it is going to collapse. Up to that point, it can take the load. Okay, for a fixed beam. That is the first type and simple one. That is your beam mechanism. And the next one is called sway mechanism. Sway mechanism, also known as panel mechanism. Okay, so it is happening in a frame structure. Frame. Suppose we have a small frame like this. Both supports are fixed. Let us say I am applying some load P. So what is the static indeterminacy of this frame? 6 minus 3, 3. So the number of plastic hinges to form the mechanism, that is 3 plus 1 equal to 4. So in this case, the plastic hinge will be forming at the joint. So 1, 2. So it will have say like this. So whenever we have horizontal load, this joint will have like peak moment. So one hinge will be forming here. Finally, we'll have 1, 2, 3, and 4. It is called panel mechanism. So or sway mechanism. It is due to lateral load. So it is due to lateral load. Okay. So this is known as panel mechanism or sway mechanism. So there are other types of mechanism also there, like I think I have a slide. So another one is this type of gable mechanism. We'll say here actually the roof is some um, inclined roof. Okay, so that type of frame, gable mechanism. So another one is called joint mechanism. It is called joint. Okay, joint mechanism. It's happening at the joint. Okay, it is due to the action of moment, and the number of members are meeting at the joint. And the number of members, there may be at least 3 or more number of members. So then the plastic hinge will be forming at all the members. So I have 4 members. So plastic hinges are forming in this member and this member, this member. Okay, so then this joint is completely failed. That is called joint mechanism. And it is called sway mechanism. These are called beam mechanism. So beam mechanism, it will also happen in your frame structure also, like this. And suppose you have a frame and you have some loading. So for this column, for this span alone, if you take, we can consider a beam mechanism in this column. Okay, so beam mechanism basically, it is not like it will happen only in the beam. It's not like that. Okay, so we can take like this. The beam mechanism So I will write one sentence. So all the loaded span, all the loaded span behave as a beam. So we'll take individually one by one span, then we'll analyze it. So we'll find out how much load is required to have the collapse in that span separately. Okay. So as all the loaded span behaves as a beam, mechanism. Okay. So these are the different mechanism. One is called beam mechanism, second one is sway mechanism, and third one is gable mechanism, and another one is joint mechanism. Okay. So these are basically the we can say that independent. Okay, these are the independent mechanism. This is happening only for the beam each span, that is a beam, and it is happening due to horizontal load, lateral load. Okay, it is happening only at the joint, and also we can have another one is called combined mechanism. So this beam mechanism and the sway mechanism, it can happen together. Okay, that case also we have to check. Actually, while finding out the collapse load for a frame, what you have to do is you have to check all the possible mechanism one by one. Then we have to take the least load. Okay, and another I would say these all are independent mechanism. Beam mechanism, sway mechanism, that is a independent mechanism. That is we have to see separate. And another one is called combined mechanism. Combined mechanism. So these all will explain. Okay, in the numerical, so it will be combined mechanism. Simply you can say that it is a combination of beam mechanism plus where sway. Okay. So like this. Suppose if you have a frame and the load is acting at the joint, and maybe here also. So there may be a sway like this, and then it may go like this. Can be something like this. So it is called combined mechanism. So we will be having again static indeterminacy is 3. So the number of hinges should be 4 plus the hinges. So there may be one hinge here, maybe one here, and one here, and here. So this all we'll see in the numerical example. So this for example 1, 2, 3, 4. Okay. So this is called combined mechanism. It is a combination of your beam and sway. Both are happening at the simultaneously. Okay. And the beam and sway mechanism. Beam and are independent mechanisms. So you can combine these two independent mechanisms to form the combined mechanism. Okay, and one more point is there that's also used to ask. So all this will demonstrate. Okay, in the numerical example, I will take everything and I will explain there also. Okay, and the another point is like number of independent mechanisms. How many mechanisms are possible in a structure? That question also used to ask. Okay, the number of independent mechanisms. How many mechanisms? Suppose if you have frame structure given, how many mechanisms is possible? Okay, that is given by so another equation n minus r, and where your n is the number of possible plus hinges. Number of possible plus hinges in the structure. Wherever the plus hinges is possible, how many plus hinges may be possible? Like okay. the number of possible plastic hinges in your structure, that is your n, and R is nothing but your degree of static indeterminacy. So it is the degree of static indeterminacy. That will give you this many number of mechanisms are possible for that particular structure. So next you have to see this one, number of possible plastic hinges, where the plastic hinges will be forming. So what are the possible locations that we have to see? Okay, that will I give you here the possible location for this is simple equation again. This is the n is the number of possible plastic hinges that we will see now, and R is the indeterminacy, and n minus r, that is the number. This many number of mechanisms are possible for that structure. Because in a given structure, the mechanism is possible, maybe the same mechanism may be possible. So like that. Okay. How many mechanisms? In some, suppose if we have a continuous beam, three span beam. So there may be three beam mechanism may be possible. Okay, not only one. There can be more than one beam mechanism. Okay, so like that we can find out. The next one is possible plastic hinge. Location, possible location for the plastic hinge. Okay, so this is where the simple understanding where how the plastic hinge is forming. Your moment has to reach MB. Okay, so wherever the moment is wherever you have a peak value moment, that point your possibly your that location you have a plastic hinge. If you increase the load, only at that location you will have the plastic hinge. Okay, and at first part is you can say that at the fixed end. At the fixed ends, because the fixed end always will have some moment, so that may reach plastic. That is a possibility. Okay, so I can give you an example, like we have a frame. These ends are fixed. These ends are fixed. Okay, I will give you that. I will explain that. And second one is at rigid joint. Okay, I will just write, then I will show you. At the rigid joint. And third one is internal support. So if you have a continuous beam, at internal support, the plastic hinge may form. That is a possible location. Internal support. And fourth one is change of cross section. The change of cross section. And the next one is the change of material. And the next one is the at the point of maximum bending moment. At the point of maximum bending moment. Let us take some structures. Then say here it is a continuous beam, and another beam is like this. So maybe another one is another beam like this. So this part may be concrete, and so I'm just giving an ideal situation. Okay, and the first point is at the fixed end. So these locations, the plastic hinges are possible. Okay, so that is the first type. And second one is at the rigid joint. So this is a rigid joint. So the plastic hinges are possible. It can form at the joint also. Okay, so this is the possible location. And the next one is internal support. Suppose if you have if you have a continuous beam, this continuous support also will have some moment, that there will be having hogging moment, so that also may reach plastic. These are the possible locations. It does not mean that the plastic hinge must form there. Okay, so wherever the maximum moment is there, that point only will reach plastic moment first, and the next it will go to the next peak, like that only it will reach. Okay, and then the next possibility is wherever we have a change of cross section. Suppose if we have a beam like this, and this moment of inertia is different, or cross section is different here at this junction. Okay, and there a plastic hinges it can form. Okay, so this is also possible location we have to consider in the analysis. And another one is change of material, something like this. At that section, plastic hinges can form. Okay, so another one is at the point of maximum bending moment. Okay, so that means suppose we have a if you have a beam, if you have a beam, simply supported beam, and I have some point load here. So the moment, bending moment will maximum at this point, at this section only. So the moment diagram will be like this. So not at the midspan, the plastic hinge will forming here. That is the sixth type. Okay. So these are the possible locations where the plastic hinges can form. So by using these, we can find out the value of n, the possible location for the given structure. Then I can find out the number of independent mechanisms. Then I can analyze that many mechanisms, and then I can find out the collapse load. So that will be the procedure we will be following in the in your numerical examples. Okay. So these are the different. Uh, so these are the different possible locations for plastic hinges. So even though your beam is having something like this, the cross section is changing. So we have to consider that point also as a plastic hinge for the analysis. Okay, actually what we are doing is we will assign. Suppose you have a fixed beam. Okay, we will do all this numerical. Then it will be, we have a fixed beam. Okay, so I have some point load that may be acting here. So my objective is I have to find out the collapse load. So I will be assigning the plastic hinges for some three locations, maybe 1, 2, and 3. Then I will analyze, I will get a collapse load in the first analysis. Okay, in the first analysis, I will take 3 hinges because for a fixed beam, I need 3 plastic hinges to form the mechanism. First hinge I will keep here, second hinge at this point, and third hinge here. And I will analyze it. I can get one value for collapse load. So I will get one value for collapse load PC. Okay. And then next I will do one more analysis. I will assign one plastic hinge here, second plastic hinge here, and third plastic hinge I can assign below the point of below this concentrated load, because that is also a possible location. The plastic hinges can form. This is the point now, the maximum point of bending moment. Moment is maximum at this location, so that is also a possible location. So that means in this case, in this simple example, I have to check two mechanisms. The first mechanism is one hinge here, second hinge here, and third hinge here. That is the one mechanism. And in the second hinge, second analysis, second mechanism, one hinge here, second hinge will be here, and here no hinge, and the third hinge will be here. So then I will combine these two analyses, and I will take which mechanism is giving the less value for the load, and that load I will take it as collapse load. So my load in this the load in this structure should not exceed that value, that least value. Okay, that is what we will be doing in the theorem analysis. That is why I'm just writing these are the possible locations. So we have to consider all the possible locations. That is why there can be more than one mechanism. Maybe we have to solve it. And if you take a discontinuous beam and we have some loading, so I can take a beam mechanism for the first span, and in second analysis I can consider a beam mechanism in the second span, and in the third analysis I can consider a beam mechanism in the third span, and each will give a different value for the load, collapse load, and I will take finally the least value, because even though this continuous beam only one span is getting collapsed, then also that will also make your structure unusable. Even though this span is collapsed, okay, these two span there is no failure, but still I will say the overall your structure has collapsed. It has become the unusable state. We cannot use that. We have to repair that part. Okay, that is why if we have a continuous beam or we have a frame or structure like that, and if any one span is failed, then that we will take that is a failure of your structure. That is why we have to check all the possible mechanism, beam mechanism, sway mechanism, or combined mechanism. And after that, finally, we have to take the least value. Which mechanism is giving the least collapse load? That only we have to that only we have to consider as a collapse load. Okay, the least value from all the possible mechanisms. So that is why all this will be applying in the numerical example. How many plastic mechanism we have to how many mechanisms we have to check, how many mechanisms will be there. So everything we have to check. We should not miss any possible mechanism. Okay, then we will be getting a wrong answer. Okay, so if the number of plastic hinges are equal to r plus 1, then what it indicates, then your total collapse, the complete structure has collapsed. Okay, and if the number of plastic hinges are less than r plus 1, then there may not be a total collapse, but there may be partial collapse of your structure. A part of a structure may be collapsed, but it may make your structure is useless as a whole. Okay, that is what I was saying. Suppose if we have a continuous beam, let us take this is my, so I have a continuous beam. Okay, so in this case, let me take one more span. So what is the static indeterminacy? 2, 3, 4, 5 minus 2. Static indeterminacy will be 3. And how many number of plastic hinges are required to form a mechanism? That is 3 plus 1. 4 number of plastic hinges are required to form the mechanism. Okay. But how many mechanisms are possible here? The number of mechanisms are possible as per this slide. The number of independent mechanisms, that is n. Okay. So number of mechanisms possible, that is the number of mechanisms, that is equal to capital N minus R. So what is the capital N? That is the possible location for the plastic hinge. So let me take some loading. Let me take some loading like this. So then what is the value of N? N is the number of possible location for the plastic hinges. So one hinge is possible here. So maybe one hinge possible here, one can form here, maybe here. Okay, and this is also possible location below the point load. So maybe 1, 2, 3, 4, 5, 6 locations. And here any plastic hinge will not form. It is a simply support. So moment is 0. It's already hinge support. So moment plastic hinge will not form. So N is equal to 6. What is R? That is the static indeterminacy, that is 3. That means the number of mechanisms. The number of mechanisms, that is equal to 6 minus 3. So in this case or in this structure, there will be 3 number of independent mechanisms. Okay. What are the 3 independent mechanisms? Can you tell me what are the 3 independent mechanisms here? The first one is we can have a beam mechanism may be formed here in the first span. It is possible. This span will collapse. Okay. In the second stage, the next mechanism may be in this span. A beam mechanism is possible, and similarly here also in this span a beam mechanism is possible. Plastic hinge will form like this. That is, we have to analyze these 3 mechanisms individually, and this will give you one load for the collapse load. It will give you another load P2. It will give you another load P3. Finally, your final collapse load for your structure, that will be the minimum value. The minimum value of P1, minimum value of P1, P2, and P3. Okay, that is what we have to do in the analysis. That is the meaning is, what I am trying to say is, even though this 2 span there is no failure, this is my structure. Okay, and this span has collapsed. This part is failed. It has failed. And these 2 part there is no failure, but still I would say the structure as a overall my structure has failed because it has become unusable. We cannot use this structure because one span is failed. Okay, that is why we have to take the minimum value. Okay, so that is we have to take the minimum value from all your analysis. We have to take the minimum value, and that should be the collapse load. Okay, and how to do this analysis, that we will be discussing in the lower bound and upper bound theorem.